So yesterday we learned about two types of discontinuities, right? The holes, which is when you get 0 over 0, and the vertical asymptotes, when you get non-zero over 0. Today we're going to learn the last of the discontinuities for which you're responsible, and it's called a non-removable jump discontinuity. It's a jump discontinuity, okay? And we're going to use example 9 as an introduction to how we can spot them, all right? If you look at this function, f of x equals the absolute value, that's what we say, of 5x minus 15 over x minus 3. First of all, let's think about the domain. I'm not going to show all the analysis because we should be able to spot it quickly. There's no square roots, but there is a denominator with a variable. What value of x is off limits? 3. X can't be 3, okay? So we're going to come over here and we're going to say the domain of f is the set of all x such that x is not 3. Now, because it makes the denominator 0, we'll say that f has a discontinuity at x equals 3. And if we use our little trick from yesterday to determine if it's a hole or a VA, I'm not going to factor and divide out because the absolute values prevent me from dividing anything out. But I can, bless you, I can plug into the top. What do I get when I plug a 3 into the top?
0.
I get a 0 as well, right? So if I plug into the top and the bottom and I get a 0 in both, 0 over 0 usually means what? It's a hole. And this is going to be 99, whoops, that's a bad 9. 99.9% of the time. The tenth of a percent that it's not is this case right here, okay? And I'll show you. It's easy to spot because it's going to have the absolute values. And it's going to be even easier to spot after you see what we do to answer this question. We're going to decompose it into what's called a piecewise function, all right? A piecewise function, if you jump down to example 10, has this very characteristic look. It has an open brace, and we're saying it's kind of like a computer program. It's like an if-then statement. If x is less than or equal to 0, we're going to use the graph of x minus 1. Else, or otherwise, we're going to use it when x is greater than 0. We're going to let it be the graph of x squared. So it's kind of like a hybrid graph. It's like a centaur, right? It's like part horse and part man. And instead of changing it the torso, it changes at x equals 0. Those are potentially going to be the jump discontinuities, right? Now let me show you how we could decompose this. Let's go ahead and first look at, let's just write it again. The absolute value of 5x minus 15 all over x minus 3. I can factor a 5 out inside the absolute values, if you notice, to get that. Now, because the 5 is a constant multiple, I can actually pull it out of the absolute values as long as I make it positive, which it already was. Now, that looks a little bit better because then I don't need the extra parentheses. Here's where I'm going to decompose it, all right? I'm going to say that depending on the value of x, I need to learn how to take the absolute value myself. So let's come over here to the side and think about the absolute value of x minus 3. If you had to write a computer program that told the program itself how to take the absolute value of x minus 3, you would ask the user to put in an input of x, right? Input x, boom. And let's say the user inputted a 1, right? What's 1 minus 3? Negative 2. How would you tell the computer program to make a negative 2 positive? What if you can't use the absolute value? What would you tell it to do? Well, if you square it, you're changing the value. We just want the negative 2 to become a positive 2. Times it by negative 1, right? Multiply by negative 1. So if you put in a value of x here and it ends up being a negative number, you would tell the computer, hey, if that ends up being negative, just multiply by negative 1 and report the answer, right? Otherwise, if you put in a value like 5, let's say we put in a 5, what's 5 minus 3? 2. That number is already positive, so you would tell the computer program, if that number ends up being positive already, no need to multiply by negative 1, just report it as is. That make sense? Okay, so a piecewise function is nothing more than a blueprint for a computer program. So I need to know for what values of x then is x minus 3 positive. Well, we'll set up this inequality. X minus 3, oops, I gave it away. X minus 3 is positive. It's great when it's greater than 0, and that's when x is greater than 3. So that would be part of your computer program. If the user inputs a value greater than 3, you're going to report the number as is. Otherwise, if the user puts a number in that is smaller than 3, you're going to tell the calculator or the computer program to multiply it by -1 to make it positive. Okay? So that's what we're going to do. We're going to decompose this. The 5 is just along for the ride times the x minus 3 is still in the bottom. But I'm going to come over here. If x is greater than 3, x minus 3 is positive, all I got to do is take it as is, right? In other words, I'll just drop the absolute values. So let's again see what this means. You can read this as if x is greater than 3, the absolute value of x minus 3 is just what? It's just x minus 3. We just drop the absolute values. Okay? Otherwise, if x is less than 3, we're going to have the 5 here and the x minus 3 still here. How do we make x minus 3 positive? Well, if we can't use the absolute value, already talked about it, we do what? We put a negative in front of it. Now notice I put brackets there. It's just another grouping symbol. So if x is less than 3, the absolute value of x minus 3, to make it positive, we take the opposite of x minus 3. We multiply it by -1. Now what about if x is 3? If you plugged in a 3 up here, 3 minus 3 is 0. What's the absolute value of 0? 0, right? Which is okay. But is 3 even in the domain of this function? Is it? No, we already said that it's not. And the reason that we wouldn't include it in here with an equal sign anywhere is because it makes the denominator 0. So if the user put in a 3, the computer program would have to put out a script that says invalid value, not in domain, choose another value or something like that. We're not going to use it. Okay, cool. Let's go ahead. We're going to do a new column here. If you ever work straight down and you run out of room, don't start working left to right. Just start with a new column, all right? Now, I want to bring all of this, and I'll just copy and paste it over here. The reason I want to rewrite it is because look what happens now. This x minus 3 in the bottom, if I put it in parentheses, does what with the x minus 3 in the top? It divides out. And that leaves us a what? A 5. Okay? When x is greater than 3. What happens to the x minus 3's in the bottom part if you put the bottom in parentheses? They also divide out, and that leaves you a 5 times the -1, which is what? -5 when x is less than 3. Holy moly smokers. We now have a distilled version of what this function is. If you put in any value of x other than 3, it's either going to end up coming out every time to be a 5 or a -5, every time. It's a 5 if you plug in a value greater than 3. It's a -5 if you plug something in less than 3. If you plug in a 3, it's not in the domain. We can actually graph that function. Let's graph that function. I'm still trying to re-navigate these buttons here. They moved them on me. All right, so here's 3 right here. This is how you graph a piecewise function. You go to that spot where it changes from one to the other. To the right of 3, it's going to be +5. So I'm going to mark that as 5. I'm going to put an open circle because it's not inclusive, and I'm just going to draw a horizontal line to the right. That graph is a 5 everywhere to the right of 3. And then down here, I'm going to put a -5 and an open circle, and I'll draw a line to the left. And that's what the graph looks like. That's what the graph looks like. Anything to the left of 3, okay? Like over here at -5, you put in a -5, what are you getting out? A -5. What do you put out at -20? You're getting out a -5. It's -5 everywhere to the left of 3. And then everywhere to the right of 3, it's 5. So the question is, what's happening to the graph at 3? Is it a hole? Is it a VA? A VA would force these values to go up or down really quickly towards infinity or negative infinity. Is that what that graph is doing? Is it curving upward or no? So it's not a vertical asymptote. Is it a hole? It looks like a hole because we have 2 open circles. But remember from yesterday, the definition of a hole is that it is a removable point discontinuity. A removable point discontinuity. Here's what removable means again. If I give you a single manhole cover, which is all we're allowed for a function at a single point, could you put that manhole cover down anywhere at x equals 3 to make these two guys connect, to make it continuous? Bless you. Could you? There's no way to make those two guys connect with a single manhole cover. Okay? That's why we say this is non-removable. This is non-removable. We can't just put the manhole cover back down to make it continuous. So the hole is the only discontinuity that's removable. The vertical asymptote, you can't make continuous. It's non-removable. And this one is non-removable. You can't make it continuous. Now, if you had to describe a physical verb for what the y values are doing at x equals 3, when they go from -5 and then they go up to 5, you would use the word jump, I would hope, especially since we've kind of talked about it already. That is called a jump discontinuity, a non-removable jump discontinuity. Right? This is the exception to 0 over 0 being a hole. All right? Now, most of the time, you're going to be able to spot it because it's going to come from a piecewise function. Let me just say that right here. Jumps come from these piecewise functions, possibly. So you're going to be able to spot them because they have the two or they can be defined by 2 or 3 different pieces, but they have that very characteristic look. Okay, they have the open brace. So there you go. There's your introduction to a jump discontinuity. Now, this guy right here has a parent function that we're going to be studying a lot in calculus. It's the absolute value of x over x. We call that guy jump man. He's a parent function. And so this would be kind of the exception to recognizing a jump when you don't have the piecewise function. Right? This is a single equation. It's not defined by 2 different pieces, but we do know that it is a piecewise function in disguise. That's the only one, okay? Otherwise, it's going to be a piecewise function. All right, so now we've seen all 3 discontinuities. A hole, which is 0 over 0, 99.9, I would even say 99% of the time. We got the vertical asymptote, which is non-zero over 0, can't remove the factor. And now we have these jumps, which are going to come from possibly these piecewise functions that look like this. All right, let's move on to example 10 then. It says, graph the following piecewise functions, state the domain, and classify any discontinuities. So here's the expectation. I'm going to give you one of these, and I'm going to ask you where is it continuous, and what type of discontinuities do we have. Now, the first thing you want to do is look to see where it changes. This is going to be some type of graph to the left of 0 and at 0, and that's going to be another type of graph to the right of 0. These 2 intervals right here, they can't overlap. They have to be distinct intervals because of the function, right? It's part line. That's the next thing you do is you look at what the actual pieces are. This is a line, which we know is continuous everywhere. And this is a quadratic, which we know is also continuous everywhere. So the only place where this graph may be discontinuous is at 0 when it changes from one y value to another. If those y values are not the same at x equals 0, we're going to have a jump discontinuity, okay? But what would be the domain? The domain of each of these 2 pieces is all real numbers. So now we look to see here if it's actually defined at 0. Is it defined at 0? The previous one that we just did wasn't defined at 3. But here it says when x is what? Greater than or equal to 0. So right there it says, yeah, x equals 0 is in the domain. It's good. So we know the domain is all real numbers to the left of 0, a line. We know the domain is all real numbers to the right of 0, a parabola. And we know it's defined at 0 explicitly in the equation, right? It doesn't give us division by 0 or anything. So the domain of this is going to be all real numbers. Now I'm going to hold off on writing that because really your first task when you have a piecewise function is to graph it, okay? And then answer the question. So let's graph it first, and then we'll answer the questions. You give yourself an x and y axis, and draw it kind of pretty because we're going to kind of be reusing this. Then you go over to 0, which is right here. There's 0. And now you sketch what the graph looks like to the left. We know it's going to be the line x minus 1. Now, if you just had to sketch the graph of x minus 1 from your Algebra 1 skills, it's in mx plus b form. You would go down to negative 1, right? You'd go down to negative 1, and you would put a dot, and then you would use the slope, which is 1, to get yourself another point, right? You would either go up 1, right 1, up 1, right 1, or you could also go down 1, left 1, down 1, left 1. I am not going to go up 1, right 1 to get the next point. You know why? Because it says we're only going to use the line at 0 and to the left. That's what less than means. So to get my second point, I'm going to go down 1 and left 1. Down 1, left. Looks right there. That looks good to you? Looks good to me. And now I'm going to draw that line right there. So that is the piece of that line x minus 1. Now, had the top piece been x strictly less than 0, instead of less than or equal to 0, I still would have gone to 0, negative 1, but instead of a solid dot, I would put a what? An open circle, because it's not inclusive. But it still gives me a coordinate from which I can start to draw it backwards. All right. Now I'm going to pick up with the piece to the right of 0, and it's my old faithful friend x squared, which we know bounces at the origin. But if you're not sure where it starts, you could actually plug a 0 in there. Even though it says when x is strictly greater than 0, what do you get when you plug a 0 in? You get 0 squared, which is what? 0. So I know it's the coordinate 0, 0. Now instead of putting a solid dot at 0, 0, I'm going to put a what there because there's no equal? An open circle. So you can use the functions to find the ending y value of one and the starting y value of the other. All you got to do is respectively put the correct thing there, either an open circle or a solid dot. Now, I don't need to get another point for x squared because I know what it looks like from there. It looks like this. So there is your graph. It's part line and part parabola. Does it still pass the vertical line test? Yeah, the only possibility would be at 0 where there's a sharing violation, but there isn't. One of them's closed and one of them's open, so that's good.
So you can't have two inclusive values.
You cannot have two inclusive values at one x value. It would violate the rule of a function. Okay? So there's what the graph looks like. Now, before we mess it up or do anything with it, go ahead and copy that because we're gonna paste it. In fact, let's do this before you copy it. Make the ordered pair at 0, negative 1. Just make it a little bit prouder. Make it a little bit darker. Make it a little bit bigger. There you go. And now we'll circle this and copy it. Okay, now that we have the graph, let's verify. What's the domain of this function? Is it all real numbers? Yeah, you can see from left to right, every x value has an output. So it's okay if you just put the double bar R. I'm fine with that. The double bar R. Do we have any discontinuities? Is there any interruption to the flow of the graph from left to right? That would mean, can you draw it from left to right without lifting your pen or pencil? No. I could draw it without lifting my pen or pencil up to here, and that what do I physically have to do to get from negative 1 to 0 to continue on? I have to lift my feet off the ground with the force of my massive quads. Careful, don't hit the ceiling. I have to jump. I have to jump from one y value to another y value. That's what a jump discontinuity is. When you jump from a particular y value to a different particular y value. This is a jump discontinuity. We would say f has you could just call it a jump at. Now, we don't list it as an ordered pair. The whole is the only one that's an ordered pair. We list it as an x value. Even though it's defined here as 0, negative 1, we just say at x equals 0, okay? At x equals 0, at that vertical location, this function has a jump. There you go. All right, and that's it. That's all we have to do. It says to verify in the calculator. I'm going to skip that for now because there is a way to graph piecewise functions on the calculator, but you know what? Today, we're the calculator. Yeah, baby, and we got it right. All right, questions on that one? That's your first piecewise function. Okay, let's look at letter B. It's another piecewise function, right? You see the open brace? What do you notice about that one and part A? they're the same except for there's no equal sign on the zero. So I can actually just do the same analysis and graph it brand new, or I can paste my graph from the previous one and modify it. What's the only modification I'll have to make here? Make this right here an open circle. So the reason I wanted you to make that kind of darker and prouder and bigger is because now all you have to do is go to your little tool and select white or whatever your background color is and just make kind of like an open circle inside there. And now you got a nice little open circle. Okay, let's talk about the domain. What's the domain of this function? Is it still all real numbers? Every x value has an output? Nope, sorry. The two pieces themselves, the line and the quadratic, their domain is all real numbers. But because it's a piecewise function, it is explicitly, we say it is explicitly not defined at 0. There is no direction for when x is 0. When x is 0, you can't do anything, okay? Are there any discontinuities? Did that change the discontinuity? Or are we still jumping from one y value to another? We're still jumping. So f still has a jump at x equals 0.
You don't have to list the horizontal jump. So like since it's going from y negative 1 to 0, you
No.
don't have to list that?
No.
It's just where
It's just the x value where it occurs. Very good. Very good. So notice, even though this one had an ordered pair at 0, -1, and this one does not, we still say that f has a jump at x equals 0. We don't list the y value. There is a way to talk about the y values, but it's coming up when we talk about the limit. There's a limit notation that we're going to learn, and we'll talk about the y values when we get to that. Okay, right now it's just the x value location. The only discontinuity that's an ordered pair is the whole. And remember, we find that y value by factoring, dividing out, and then plugging into the simplified version. All right, look at letter C. It's definitely a piecewise function. This one, though, is a three-headed baby, right? A three-headed baby. Kind of terrifying, but still could be cute, right? Oh, look, three-little-headed baby. Creepy, but cute. This is the same as the previous one when x is less than 0. And the bottom piece is the same as the previous one when x is greater than 0. But now we have this middle piece that explicitly says, hey, when x is 0, call it what? 1. Call it 1. So if you want, you could go ahead and paste the pretty picture from part A. You can modify it by putting a white hole at 0, -1, or you could just copy the previous graph if you want. I'll just make the open circle again. And now it says the middle piece, when x is 0, call it 1. So I'm going to put a line here, call that 1, and I'm going to put a solid dot right there. That is a piecewise function. Does it still pass the vertical line test?
Yes.
It does, right? So what would be the domain of f now? It's back to all real numbers. The line takes care of everything to the left. The quadratic takes care of everything to the right. And now we have reintroduced 0 back into the domain by saying it equals 1. Wow, way to go. So the domain is back to all real numbers. Are there any discontinuities here? Yes. Is there still a jump at x equals 0? Yeah, f has a jump still at x equals 0. Now, when we graph this function from left to right, we call it a jump still because we're jumping from -1 to 0. We're not going to say that we're going to jump from -1 up to 1 and then back down to 0. We're just talking about how we would continue the graph coming in and out. We're coming in from the left to -1 to continue on to the other side. We jump up to 0 and continue on, okay? It just so happens that there is a dot up there. If you want to think about like crossing a canyon with a road, a bridge, and a road, you're driving on the road, there's a canyon ahead. To get to the other side, there's a bridge, right? And then when you get off the bridge, hopefully there's a road that exits the bridge. In order to drive across, you would need the road coming in, the bridge, and the road going out, but you would also need them to all be what? Connected. Yeah, if they're not connected, that's no good. Here, we have a road coming in, we have a road going out, And we have a bridge. But oops, are we going to be able to drive across? No, because they're not connected. This was a horrible construction project if we were trying to build a bridge across the canyon. We got a road, they're not connected, and we got a bridge, but it's somewhere else. Not good at all. But we still say that there's a jump at x equals 0. And it's because the y values jump from -1 to 0. Okay, let's look at the last one here. We have x minus 1 now when x is less than or equal to 0. That is the same as part A, right? But now we have not just x squared when x is 0, we have x squared minus 1. What would that minus 1 do to the graph of x squared? By transformations, if it's on the outside, it moves it down 1, down 1. So let's go ahead and paste our graph from part A. We'll paste our graph from part A. And now we'll just pick up this parabola and the hole that's there. And this is cool with Notability because you can animate it. And I'll just pick that up and move it down. Oh, I got the x-axis. Okay, I didn't want the x-axis. There we go. I'll just pick that piece up and move it down 1. What happens to the open circle when it gets to the solid dot? They become 1, don't they? Like husband and wife. That's the only time 1 plus 1 equals 1, right? In marriage. They become 1. That open circle lassos over the solid dot. And now, what have we done? Have we eliminated the discontinuity? We have. We've made it. We've fixed the construction project here. We could drive across safely. What would be the domain of this function? It's still all real numbers. And is there a discontinuity? No. So we would say f now is continuous for all x. F is continuous for all x. So just because you have a piecewise function does not mean you're going to have a jump. You could have a hole. If I remove the equal sign up here from the 0 and it was just less than 0, now I would have a hole instead of a jump. Because now the y values would be the same on both sides. It would just be no bridge there connecting them. Okay? So piecewise functions are kind of cool because they're either 2 for 1s or 3 for 1s. But we can make any of the 3 discontinuities appear. All right? So that's piecewise functions. But for the most part, if you ever have one of these types of functions, back from example 8, if you ever have a polynomial over a polynomial, and there's no absolute values in the top, and there's no brace to show that it's a piecewise function, that's when you're going to get a hole every time when you get 0 over 0. The only time 0 over 0 might be a jump is when you have absolute values on one of those, or you see the signature open brace, which tells you it's a piecewise function. And because it's a piecewise function, you can program it to do whatever you want, or I can program it to give you whatever you want. It could be a jump, a hole, or a VA. The key to piecewise functions, though, is in graphing them. Okay, so when you're graphing them, do what we said. Go to the point where they change, graph it to the left, graph it to the right. And they're going to be basic functions that you should know from Algebra 2 and real basic transformations that you should know from Algebra 2, like down 1. Okay. All right, I think we finally finished 2.1. What a behemoth of a section that was. So just to review then, the worksheet for 2.1 is due when? Thursday. That's tomorrow at 9 a.m. into Canvas as a PDF. It only accepts PDF. Okay. We are also going to take a quiz tomorrow. Yeah, anytime we have a worksheet due, you can expect a quiz. Just to see how well you obtain things from your worksheet. All right, and then, of course, tomorrow in the quiz, instead of being like example whatever it was before, it's going to be mainly on discontinuities. So your quiz tomorrow will be mainly like example 8 and example 10. Okay, let me write that on there. It'll be quiz tomorrow like example 8 and example 10.
And is it going to be a free response or?
Yeah, your quiz is always short answer. So again, different from Algebra 2. First of all, your quizzes are like 2 problems. You'll have 2 problems mainly. One from example 8, one from example 10. You'll have like 10 minutes to do it. and then we grade it immediately afterwards. It takes another 5. So quizzes in here only take 15 to 20 minutes. That's it. We pass them up, and then after that 20 minutes, we go on to the next section. It's not like Algebra 2 where you have the whole period to take a 10-question multiple choice test, and you finish it in 20 minutes, and you go back to your desk for 30 and fiddle your thumbs, right? It's a little bit different, but it works better, I think. You grade it yourself, you get the immediate feedback, and then we move on. That's what we're doing. We're about moving forward, learning new stuff, learning new things. All right, we got 4 minutes left in class. Anyone have any good, clean jokes? Like, why did the crab blush? Because it's all the bottom of the ocean. It's all the ocean's bottom. Yeah, yeah, yeah. Why did the ketchup blush? Because it's all the salad dressing. It's kind of in the same vein there. It's all the salad. It's all the salad dressing, right? Yeah, yeah. See, so you really hope in the future we don't finish early. You would like to go with math the full time and not these dumb jokes, right? But we are done. We are done.